thank you so much for the invitation to speak here, and I wish you all a good morning or good afternoon. And I will actually somewhat pick up where Tanya stopped, because I will tell you about how we model the nonlinear regime of gravity that unfolds as black holes or neutron stars merge, and we use numerical relativity to do so. I will focus on using numerical relativity to model effects in extensions of general relativity. So that goes towards testing gravity in the nonlinear regime. Let me start with some introduction first, though, because we are now in a position where we really have of the order of 100 gravitational wave detections from black hole, neutron star, or neutron star black hole mergers. So this is a plot by the LIGO-Virgo collaboration from the end of last year, where you see here on the x-axis the masses of the compact objects ranging from 1 solar mass down here up to 200 solar masses up here. And this is the range of detections that we already had. In blue, black hole detections, here in orange, the neutron stars. And I like to show this plot because this is really impressive. If we think back just a little more than 6 years, we had the first detection, which was this really big breakthrough. And now with almost 100, we are really entering an era where I would start calling it the precision science. We are starting to have precision gravitational wave detections. And that means that we can use the observations of black holes, neutron stars, and the gravitational waves that they emit during their late in-spiral and merger to search for new physics. So we can use them as gravity detectives, if we wish, to understand physical phenomena. Also, if I look forward, there's a huge discovery potential to be done. So I give you just one example here from the Cosmic Explorer Horizon study from the end of last year, listing some of the exciting physics that we can do with the black hole detections that we already have, and that will come with much higher precision, with much higher signal to noise ratio in the next decade or next decade and a half. So one big block here is, of course, the physics of black holes and neutron stars throughout cosmic times, right? So how did black holes first form? How did the first galaxies form? And what is their population? One thing that is not listed here, but is also important, is can we solve, for example, the H0 problem using observation of gravitational waves from compact objects? Another big topic that Tanya already touched upon is to learn about dense matter inside neutron stars and actually help us understand questions in nuclear physics, nuclear theory. And the last block here that I want to focus on today is about the nature of gravity itself. What is, is general relativity actually the ultimate theory of gravity? And from theory trying to combine gravity and quantum physics, we know that general relativity is not a good candidate. So at some point, there need to be extensions to general relativity, and these current and future gravitational wave detections may hold the key to study that. You may also learn more about dark matter, dark energy. I will have one example touching upon this dark matter question. And you may wonder whether or not the compact objects that we observe are really black holes, or are they some more exotic objects that are just mimicking our black holes. Yeah, so this is what lies ahead. And what I want to focus on today, as I said, is this last, this big topic here. And I want to focus on numerical relativity, where we study the merger of compact objects. And before actually going beyond GR, let me just remind you where that falls into the bigger picture, even within general relativity. And for that, I'm showing you here a plot from the discovery paper in 2016 for the first gravitational wave detection, where we have here the strain as a function of time. This is a numerical relativity simulation for this very first gravitational wave detection, DW 150914. And here you have the kind of early in spiral phase, where the objects are still far apart, and you can use the PostNewtonian descriptions, that is this expansion in weak gravitational fields and low velocities that you've already seen in Tanya's talk. Then for the merger here, you really need numerical relativity calculations, because your equations become nonlinear and you need to solve this fully numerically. And then here, after the merger, our black hole will settle down to a single rotating black hole and emit quasi-normal modes as you do so. And so in this last bit, you would use either perturbation theory, or you can also use numerical relativity. And what I want to highlight here is that you really need all these three kind of core techniques to get a complete in-spiral merger ring down signal. And as you've seen in Tanya's talk, you would use numerical relativity, for example, to calibrate effective one-body waveforms. If you are more familiar with phenomenological waveforms, you would join together post-Newtonian and numerical relativity waveforms. And creating these theoretical templates is really crucial to interpret the source parameters of our signal. So in general relativity, that would be the masses, the spins. If you have neutron stars, maybe the equation of state. If you go beyond GR, that would also involve having a way to interpret and probe which theory of gravity you may have. Good. And before I go actually to beyond GR, let me just give you a one slide overview. What are the key ingredients in numerical relativity? I know that Harald is going to give a talk later in this meeting, so I will only focus on the basic ideas and then move on to numerical relativity and extensions of GR. Good. So what do we do in GR? Let's write down first Einstein's equations, which is this beautiful, diffeomorphism invariant theory, connecting geometry here through the Einstein tensor with matter here on the right-hand side. What we do in numerical relativity, and if I say numerical relativity, I mean performing time evolutions of our compact binaries in 3+1 dimensions. So we actually split up again the dependence on spatial hypersurfaces parameterized by a time coordinate. Yeah, and if you do that, you will find one set of equations that are elliptic type partial differential equations. These are constraints, and you usually solve them to get consistent constraint satisfying initial conditions. The second big part that you will get are evolution equations. So these are hyperbolic type partial differential equations that we supplement with gauge conditions, that is conditions on our lapse and shift on our coordinates, if you wish. One thing that is crucial, and that's why I typically like to list this here, is that this combined system of these time evolution partial differential equations plus these gauge conditions need to give us a mathematically well-posed initial value formulation, because that's a necessary condition for numerical stability. So if that's not given, then it's almost not meaningful to even start an implementation, because you know that the numerical evolution would become unstable. Yeah, so you want to make sure that this is given, and this is actually some of the longest part in some extensions of GR to get this right before you start an implementation. And then the last big ingredient component is, of course, diagnostic tools, because once we've done, or when we are doing these simulations, we also want to understand the physics. So we want to extract gravitational wave models, or if we modify Einstein's equations, any additional radiation channels. So this goes under wave extraction. We also want to understand the properties of our compact objects, and we typically use apparent horizon finders to do that. That allows us to monitor the apparent horizon at each step in the evolution, which is in contrast to the event horizon, which is a global concept where you would need to know the entire space-time. Yeah, so apparent horizons are local in time concepts that allow us to monitor during the evolution. Now, it was in general relativity. If I look back to the first paper back in the late 1960s, to the breakthrough, the first one orbit or 1.5 orbit and merger of two black holes in 2005, this took the community about 30 years. So this breakthrough was by Franz Pretorius in 2005, and then we have the group who's now in Rochester, and the group in Goddard who had a different formulation in 2006. Luckily, we can build upon the experience and learn from some of the challenges, and one of the big challenges actually was this well-posedness. So that's why I've highlighted this here. So we can learn from that if we want to go beyond Einstein's equations. Yeah. So nowadays, realistically, if you say, okay, I want to model this particular theory of gravity, to start from there all the way to have the first proof of principle simulation of a black hole binary typically takes 2 to 3 years. Yeah, and that includes both a mathematical understanding, initial conditions, so that's solving these elliptic partial differential equations, and understanding the hyperbolic problem. And then, of course, the implementation, which and running, which can be an entirely different beast sometimes. Good. So, and the reason why we are interested in that is that we want to understand what is the signature of our compact objects when they merge, and if gravity is extended beyond general relativity. And here I'm actually showing a plot which is from pre-breakthrough in numerical general relativity. So this is a plot by Kip Thorne, where he shows the inspire. So it's the equivalent plot of what I had before, where we already have an understanding of the dynamics from PostNewtonian models. People also have already studied, to quite some extent, the ring down if you go beyond GR. And for a long time, this merger regime was a big question mark. And again, you might ask, as Kip Thorne did back in the day, what is the signal like? Is it something really wild as it is here? Or is it something very smooth as it turned out to be in general relativity? And again, to understand that, we need to do a little bit more work, extent of what I showed in the previous slide, and go beyond general relativity. And that's what I want to do in for the rest of my talk. I will give you one flash slide of the current status where we stand right now. And then I selected 5 examples to give you some idea of new phenomenology that we identified with performing numerical simulations of compact binaries in extensions of general relativity or extensions of the standard model. So the flash slide is this one. You don't have to read through this in detail. I just show this because it nicely shows the progress that the community has made over the last few years. So the very first studies go back about 10 years and were basically done in scalar tensor series. And most of the other papers you see are basically from the last, at most 5 years, looking at single black holes, single neutron stars, and how black holes might form in varieties of theories. I'm not going to write down the actions here. Then, of course, compact binaries is what you need to study if you want to make connections to gravitational wave observations. And there has been quite some progress. And again, you can see this is all very recent. And I actually on purpose put here as of March 2022, because I already, since the last talk that I gave about a month ago, could add a few more new results. And then the last part here is the question of whether or not our black holes that we observe, or the compact objects that we observe, are really black holes, or could they be something else? Could they be boson stars, scalar boson stars, progress stars, etc. If you see yourself missing here, please reach out to me. I will try to keep this as complete as possible. Yeah, so don't hesitate to reach out. And I think I saw a raised hand, so maybe I can stop here for a minute and take a question.
Yes, so my question is, these corrections over this GR waveform, are these perturbative corrections, or these are nonlinear corrections? These theories?
So that depends very much on the theory. So I will give you two examples that fall into this class scalar tensor theory, where you can actually solve so this would be to solve Einstein's equations plus equations for a scalar field coupled in a particular way to matter. And these equations are pose a well-posed initial value problem. So you can solve them in full non-linearly. The second set of examples will fall into this class here, which I would combine as quadratic gravity. So one will be a dynamical Schoen-Simons gravity, one is scalar Gauss-Bonnet gravity, where until quite recently, people mostly worked in an expansion in the series. So where you treat, GR as your leading order, and you have a higher curvature correction, and you make that kind of effective field theory formulation explicit. There's a couple of recent work by Will East and Justin Ripley, where they use the formulation where they don't have to make this expansion explicit. Yeah, maybe one thing that I should say though, and thanks for the question at this stage, in numerical relativity, we have to implement a specific set of equations. So in that sense, we cannot use a parameterized approach as straightforwardly as, for example, it is done in parameterized post-Newtonian or parameterized post-Einsteinian techniques. Yeah. So does that answer your question?
Yes, thank you.
Okay, very good. So thanks a lot for that. Yeah, and as I said, I will now go over a few examples, focusing first on scalar tensor theory, and then the second half will be these quadratic type series. Good, so let's get started. And that's the first slide here for scalar tensor series, and I'm particularly interested here in neutron stars. And I'm not going to write down the action, but let me write down the scalar field equation up here, where we see that the scalar field actually obeys some kind of Klein-Gordon equation with an effective mass term, where B is a parameter and T is a trace of the energy momentum tensor for your neutron star. And it turns out that if this, so this B times T basically gives you an effective mass squared. And if that effective mass squared becomes negative, then tachyonic instability is triggered, and your neutron stars can what we call spontaneously scalarize. The scalar field will be spontaneously excited once this effective mass becomes negative. And here on the left, we see one example from a paper by Masaru Shibata and collaborators, where we have the mass of the scalar field versus the mass of the neutron star for a specific equation of state and a range of these parameters B. And you see that as we increase this parameter, so we may focus on the orange line, which should be visible quite easily. Yeah, you start exciting the scalar field. Now the question that so this is, by the way, goes back to work by Thibaut Damour and Esposito Farese in the early 90s. And now you can ask, what actually happens if I put that in a binary? And people have done so about 10 years ago. So there are a series of papers, both by Shibata and collaborators and Luis Lehner and collaborators, where they have looked at two scenarios. So first scenario, this is what I will call dynamical scalarization, where we have two neutron stars. None of them harbors a scalar field, so they are both not scalarized, indicated here in this equation with S bar. And as they in spiral and get closer and closer together, once the binary is compact enough, the scalar field actually becomes excited. So in this case, you have what we would call a dynamical scalarization. Yeah, so not scalarized plus not scalarized ends up being scalarized. And the second scenario that you might have is a neutron star that is not scalarized. So as bar here, one neutron star that is scalarized, and again, as the binary becomes sufficiently compact, you induce a scalarization in the companion, and your final object is scalarized. Yeah, and again, this is shown here on the left, where the GR evolution is in black. So this is the maximum density for the neutron stars, and the scalar field here at the bottom. And of course, in general relativity, the scalar field is not excited at all. Whereas if you increase this coupling value here, this beta, the scalarization may happen earlier and earlier.
So just a clarifying small question. So scalarization basically means when the mass square becomes negative, the field starts to roll down from the maximum, and then.
Right. So yeah, what you have, if once the mass square becomes negative, you have a tachyonic instability, and then the scalar field would grow exponentially. Yes, so this is what's happening here.
Okay.
Yeah.
Thank you.
Good. Okay, so let's switch over to the next example. So in this case, I am looking at, oh, I should have written down the equation. So here I'm looking at black holes coupled to a massive scalar field. So this is not really scalar tensor series. Here I'm thinking about ultralight fields that appear in beyond standard model particle physics. And some of these are candidates for dark matter. More broadly, they are ultralight fields predicted in, for example, string Axiverse scenarios. And the exciting thing is that we can use black holes to probe for these extra particles, because the scalar field will so either form a bosonic cloud due to a process that's called superradiance, when the mass of so the mass energy of the scalar field is comparable to the black hole mass in natural units. So let me reverse that. So if the Compton wavelength of the scalar field is comparable to the size of the black hole, then you have a very efficient growth of a scalar condensate around a black hole. More recent work has shown, more recent work by Katie Clough and collaborators has shown that if you have some scalar field condensate around a black hole, even if the black hole is non-rotating, so if you don't have superradiance, it may be accreted onto the black hole and form kind of scalar charges around black hole. I'm using quotation marks here because it's not in the strict mathematical sense. So that's the phenomenology for a single black hole. So what we've done with one of my students, Giuseppe Ficara, who is finishing this summer, is to actually look at binaries of the system. And in the first instance, we are focusing on the decoupling regime. That is, for the time being, for the results that I'm showing you here, we are looking at the scalar field dynamics as sourced by a black hole binary in the background. And we've implemented that in my numerical relativity library Canuda, which is open source and available here at this Git repository, and it's fully compatible with the open source Einstein toolkit. I should also say that Canuda by now has quite a few contributors across the world who are all listed here. Good. So what we are looking at now first is, as I said, black hole binary in the background. We chose a binary that has a mass ratio of 1:2, and the situation is such that we have a joint, so a common scalar field configuration, which is spherically symmetric, that encompasses both black holes. So let's have a look how this looks during the evolution. And what you're seeing here is the equatorial plane and the evolution of the scalar field. You see that around each of these black holes here indicated by the red dots, the scalar field is accreted. So you can think of this as having two, sorry, let me just show this again. So you can think of this as having now two scalar charges orbiting around each other, and you see that they start producing scalar radiation, scalar dipole radiation. Good. So let's have a look at this radiation at the scalar field multipoles in a little bit more detail. And for that, we are actually looking here at 4 different scenarios. And by 4 scenarios, I mean this ratio, black hole mass times mass energy of the scalar field. So remember, this parameter here basically gave us a ratio between the Compton wavelengths of the field sorry, and the black hole size. So we are varying here from this number being 0.1 to 0.4, 0.6 here on the right. What I'm showing here is the energy, the magnitude of the energy density in each multipole. So what you would expect originally is that this would be dominant in the L equal M equal 0 multipole, which is our scalar charge. And indeed, for a very small coupling constant here, this is what we see. Yeah, so the scalar field monopole is dominant. All the higher multipoles are subdominant here. Now, as we increase this coupling parameter, as we go closer and closer to a value that's about 0.5, we see that the higher scalar field multipoles are also excited. So, for example, here in green, we have the scalar field dipole, which becomes actually comparable as we increase the coupling to be about 0.6. What I'm not showing here is that if I increase this coupling even further, that goes away again, and that's because the accretion onto the black hole is of the scalar field onto the black hole is particularly strong in this coupling regime, and that of course means that I have particularly strong scalar charges. Yeah, good. And this is exciting because now we have a way to use black holes and gravitational observations in the future, at least, to probe for ultralight particles with current and future detectors. So if I give you just a rough estimate here from using this estimate up here, that's a ratio is roughly 1/2, then I can take my black hole mass ranging from 10 billion solar masses, where we probe with pulsar timing arrays, all the way down to LISA with 1 million solar masses, down to just a few tens of solar masses that we probe with ground-based detectors. And we would be sensitive to ultralight scalar fields in the mass range of, well, 10 to the minus 21 electron volts with these supermassive black holes. And that's where people are interested in dark matter candidates, all the way to fields with a mass energy of 10 to the minus 11 electron volts. And that's when we get into the realm of the QCD axion. So again, there's, I think, a really compelling case to make that we can probe even particle physics with gravitational waves. I should also mention that, of course, here I've looked at the decoupling scenario. So I showed you results for the scalar field. But we are currently working with one of my new students and with Giuseppe, who's finishing, on extending our code to include the back reaction. The only thing that's still missing was this consistent initial data. Remember the boxes that I had in the beginning where I said elliptic equations for initial data. This is what they are currently working on, and they have the first successful tests here. And then the evolution we already have from different projects. Good.
Sorry,
So
I just wanted to ask a question about trying to understand the calculation. So you are numerically evolving a dynamical system where you have this asymptotically flat geometry?
That's right. That's right.
Okay, and then you are putting two masses, for example, neutron star, you probably have some model for that. You are putting that and then evolving it. How are they coupling?
So here we are focusing on black hole binaries in the background. And this background is time evolving. So we have a black hole binary that is evolving, and we have a scalar field that is sourced by that binary.
What is a black hole binary? You are putting Schwarzschild?
So in this case, we had two non-rotating black holes with a mass ratio of 1 to 2. That's right. Yeah. So I mean,
so
yes,
you start from long distance, is it? You start from a configuration where they are far away.
So we start about 10 orbits before merger. Yeah, so this is a numerical relativity calculation, and we start about 10 orbits before the merger.
Okay, I see. So the black hole geometry itself will produce an interaction between these two, is it?
Yes, that's right. That's right. Yeah. So the background is fully nonlinear. The scalar field is solved by the Klein-Gordon equation sourced by this background. Yeah. And as I said, so the next step now is to include the back reaction of the scalar field onto our dynamical binary.
Yeah. Okay. Thanks.
Yeah. Okay. Wonderful. Good. Any other questions here? Because if not, I will move on to the second part on quadratic gravity models. So this is example 3 is actually work led by Masha Okunkova and collaborators, where they looked at what's called dynamical Chern-Simons gravity. The Lagrangian is written down here. So you have the Einstein-Hilbert term. you have a axion, which I call theta here. This is the kinetic term. And then you have a coupling between the axion and gravity through this Pontryagin density here. So R star R is the Pontryagin density. Good. And if you look at the field equations, let's focus on the scalar field equation here. You see that your axion, your theta now is sourced by the Pontryagin density. The results that I'm showing here use an effective field theory description in the sense that we are taking our theory as being a GR to leading order plus this correction here. Yeah, so we use this alpha CS as an expansion parameter. If you do that, you have actually quite similar scenario to what I had in the previous slide, where you have a time evolving dynamical background described by general relativity. And now your modification scalar, or I should actually be more precise here, this is an axion field. The equation is described, is sourced by this background. And the reason why people are doing that is that the equations of motion are actually third order and time derivatives. So we currently have no well-posed initial value formulation for the full system. So what we can do is use this effective field theory approach. And as I said, the results I'm showing here is up to first order, where we have a modification to the scalar field. In the example that I'm showing here is a paper, as I said, by Masha Konkova from 2017, where they looked at 3 different black hole configurations in the background. 2 of them had initially spinning black holes, where the Pontryagin density from the beginning will be non-vanishing. I picked the case, and for a good reason, where our initial black holes were not spinning. That means initially the Pontryagin density will vanish, because that is only non-zero if you have angular momentum. Good. So if we look at the results here, let's look here at the left-hand side, we have in the top panel the gravitational waveform indicated by the Newman panel scalar psi4, quadrupole mode thereof, as a function of time. And then we have the scalar or the axion multipoles L equal 1, so that's the dipole, L equal 2, M equal 1, L equals 3, M equal 2. Yeah, and all of this as a function of time and aligned such that 0 corresponds to the peak in the gravitational waveform. Now, if you look at this evolution, and if you were to do a similar calculation, but so for the early inspire using post-Newtonian calculations, you would not expect to have any excitation in the scalar field, because the Pontryagin density of your initial black holes would be 0, because they're non-spinning. Yeah, and that basically would go through for as long as this calculation is valid. Now, what Masha and her collaborators have found is that very close to the merger, you actually have excitation of the scalar dipole and higher multipoles that you did not expect with post-Newtonian calculation. So this is one example where we really see a new dynamical effect that we would not have seen without computing the nonlinear merger regime. And this, I think I would like you to keep in mind, because there are effects that we cannot yet capture with post-Newtonian theory, and we really need the combination of those with numerical relativity to get a consistent picture and to understand new effects, new dynamical effects during the merger. I should also say that by now, Masha has extended this calculation to include second order effects in this effective field theory approach. That is, she also calculated modifications of the metric at that second order. I'm not going to show that here today, though. Okay, so, and let me now continue some recent work that I've done in my group. And for that, I will have a very brief interludium just to bring everyone on the same page. So here I will be looking at a model that's called scalar Gauss-Bonnet gravity. It's kind of the parity, even counterpart to this dynamic Simons theory. And again, we have our Lagrangian here with the Einstein-Hilbert action. We have now a scalar field. This is the kinetic term of the scalar field. And we have a coupling, nonlinear coupling between the scalar field and the Gauss-Bonner invariant. This curly G here is essentially a Riemann squared minus 4 times Ricci tensor squared plus Ricci scalar squared. With this particular combination, your field equations will still be second order in derivatives. And if you derive the scalar field equation, now we get the scalar field sourced by the first derivative of this coupling function f with respect to the scalar field times the Gauss-Bonner invariant. And what's important here is that the choice of this coupling function actually selects two subclasses or two types where black hole properties can be quite different. So let me go over these two types first and then show you results of our calculations. So the first type are those where the derivative of the coupling function with respect to the scalar field will never vanish. So examples for that are what we call shift symmetric Gauss-Bonner gravity, or we can have this exponential coupling that would be Einstein-Dilaton Gauss-Bonner gravity. Yes, this is kind of a Dilaton coupling. And in this case, if the coupling function, the derivative of this coupling function never vanishes, then you see, looking here at the scalar field equation, that the right-hand side will never vanish, and your scalar field is always sourced. And people have shown this more rigorously mathematically, that black holes in this type of theories will always have scalar here. So, and we actually did a calculation which was the first code test about 5 years ago, where I simulated that numerically, and starting even with a zero scalar field, I would see that the scalar field was always excited and actually approach the analytic solution that you would expect from solving this equation. Yeah, so this is type 1 hairy black holes. So type 1 will always have scalar charge around each of your companion. The second type, what I call type 2, can have regions where the derivative of the coupling function with respect to the scalar field is 0. And examples for that are couplings like a phi squared type coupling or an e to the phi squared kind of Gaussian coupling. And in this case, if your derivative of the coupling function with respect to the scalar field vanishes, the right-hand side here becomes 0, and you just have a massless scalar field around a black hole, which would then, even if we have a small perturbation, would decay. That is to say, the black holes of general relativity, the Kerr solution and the Schwarzschild solution, are still solutions in this type 2 Gauss-Bonner gravity. However, because of this coupling, because of this form of the coupling function, you again can have scenarios where you develop an effective mass term here. And as we've seen for the neutron stars, you may have scenarios where the black holes become spontaneously scalarized because the scalar field might grow through a tachyonic instability. Okay, so with that all laid out, let's start looking at this first type here.
Can I ask one more question, please?
So
I thought maybe I have understood wrong. The scalarization was being used to see a signature of the, in spiral through the scalar radiation, right? Because in spiral is like an instability, and therefore there is a radiation in the scalar. Is that the right way to think about it?
So for the neutron stars, what happened is that, so once the binary became compact enough, the effective mass term became negative. So there you had a constant times the trace of the energy momentum tensor. If you, so be patient for 2 more slides, and then I will tell you a little bit more what happens in this black hole case, because I think you will be in for a little bit of a surprise.
No, I just wanted to know if that was the right way to think, that the scalar radiation carries the information that the in spiral has started.
I'm not sure what you mean by started, but what happened, so what will happen, and we will see another example now, is the following, that if you have scalar radiation. So think about GR. I have my compact binary. They're inspiraling and they're emitting gravitational waves as they do so. Now, if your black hole or if your compact objects are scalarized, then there will also be scalar radiation carrying energy away from the system.
Right.
And your inspiral will be accelerated. And that will lead to a dephasing.
So what was the motivation for looking at the scalar radiation? Basically, that's what probably I'm asking.
So if you go beyond, so most models in, beyond general relativity involve a scalar field, right? And the simplest one, so the first one that I had shown you was for neutron stars in scalar tensor series, which is kind of the minimalistic extensions of GR. Yeah.
I see. Okay. I see.
Yeah.
Fine.
So this case here is different. Sorry, maybe I should have said a few more words. So this kind of theory here, what I'm showing you here, as well as this dynamical Chern-Simons theory, they come about as a low energy effective action from quantum gravity candidates such as string theory. Yeah. So here the idea is to look for the effects that higher curvature corrections may have if you have a compact binary. Yeah. Yeah. So
otherwise, you can also see from your calculation the standard gravitational radiation, right? From your setup.
What do you mean by that?
Just the metric radiation. I mean, in your calculation, that also you can calculate, right?
Oh yeah, absolutely. And I should also say that here, with the results that I will present, I will again work in this small expansion regime where I use alpha GB as a small coupling parameter. So yes, I will have GR in the background, and of course I can fully compute the gravitational radiation in the background. I'm studying the dynamics of the scalar field sourced by this background, and what you can now do, at least in the first instance, is to estimate the energy fluxes from the scalar field and the effect that that would have on your gravitational radiation.
Okay, thank you.
So that would be the next step. But for the time being, I really want to focus on the phenomenology first before going here. Yeah.
Okay. Thanks.
Absolutely. Sorry, Helvi, may I ask one more question?
Of course. Yeah.
So, so this effective theories that you were discussing now. So one is with a pointwise term with axion-like coupling, and there is this Euler term and scalar coupling, right? So, so there are probably some constraints on the parameter, the alpha, etc., coming from quantum gravity things like probably in the early 2000. With 3-loop calculation, Maldarsena and others has given some constraints that I mean, some of these theories need all other terms to make sense. All other higher curvature terms you have to incorporate. Yeah. So whether these calculations that you are doing in numerical relativity as perspective are taking into consideration those constraints and also these higher curvature terms, etc.
Okay, so we are not, so let me start with the second part of the question. So no, we are not currently including these higher order terms. As I said, we are treating this model as an expansion in the coupling and basically only taking the next to leading order term here. And the reason is a practical one, right?
Yes, I understand.
So you're absolutely right. If you wanted to do it in full glory and really accurately, you would have to take all the other terms. For practical reasons, you're focusing on the first next to leading order term to implement. And so
the other question was regarding some causality constraints on this Gauss-Bonnet parameter.
Yeah, and exactly. So this is actually one of the things that we also see, I think, in a different reincarnation, because equations of motion that you get here are not hyperbolic as we would love to have for numerical simulations. They are of a type that's called Jacobi type, where you have an equation that in some regions of the space-time is hyperbolic, in other regions of the space-time becomes elliptic. And if this coupling here is small enough, then the elliptic regions remain inside the black holes. Or in other words, you know, once this elliptic region becomes outside, is outside the black hole, you will have issues with your causality. Yeah, so that's why I say this is a different way of thinking about this.
Okay.
And then the other point that you were making is if you really say, okay, this comes from string theory, some standard models, then yes, there is a quite strong constraint, theoretical constraint already.
Yeah.
We are a little bit more phenomenological and say we are actually interested in potential effects that higher curvature corrections might have. So what's the phenomenology here? So should probably be more precise. So these terms, I would say, is string inspired, but not married. So we are not demanding that this coupling is really the string coupling. Yeah.
Thanks,
and then, yeah, absolutely. No, but that's a very valid question to ask. And I should also say that from post-Newtonian calculations, there are already some constraints, observational constraints here. Good.
Just one quick comment. I think I think I agree with your point of view, because if you say string theory, because that alpha will be related to some string parameter which is perturbably small, actually, to make sense. But
that's right.
I believe you are not going to set it perturbably small, right? You have some finite value of alpha GB. You have some finite value.
Yeah. So basically, I'm treating. So I'm doing this expansion in this alpha GB, or the dimensionless version there of alpha GB by itself has a masked squared dimension, and that basically. So if in this expansion, this alpha GB scales out, and I can treat the scalar field equation in the background of a GR binary. Yeah. So this is what I'm going to do.
Thanks.
Yeah. Absolutely. Good. Okay. Any other questions here? Because if not, I will continue and look at this first, the phenomenology that we get for this first type. So type 1, just for all of us to remember, in this case, our black holes will always have scalar charges. Yeah. So I'm focusing here on this shift symmetric type coupling, where the coupling function is just phi. Okay, so, and again, we've implemented this in Canuda. Code is open source, and I'm looking at decoupling, and I'm also focusing now on the scalar radiation. The background binary that I have will be 2 black holes, mass ratio of 1 to 2, non-rotating. And they will complete about 10 orbits before their merger. Yeah, and we're looking again, sorry, at the equatorial plane. So let me just make this a little bit big, a little bit bigger. Yeah, so we have the equatorial plane here. The color coding is a amplitude of the scalar field. We have these scalar charges around each of the black holes. One thing to note, so mass ratio of the black holes is 1 to 2. The larger scalar field bulge corresponds to the smaller mass black hole, because the curvature for the smaller mass black holes is larger. So the scalar field actually is larger as we have larger curvature. Yeah, and as you can see, as the black holes in the background are inspiraling, they drag the charges along with them, and we see the excitation of scalar dipole radiation. And now we're getting closer and closer to the merger. Black hole in the background merges, becomes a single rotating black hole. The scalar, non-axisymmetric scalar field modes get shed away, and we are left over with a hairy rotating black hole. And we checked also that the scalar field solution at this stage then agrees with perturbative, with approximate solutions, for example, by Kent, who I believe is or was here. Good. So that was one part of the numerical calculations. I should also say that afterwards, Masha had built or extended this work to second order in this field theoretical expansion. Will East and Justin Ripley actually found a way to implement the equations without the order by order expansion. I'm not going to show their results here, but I think this has been a really important result as well. So I would like to mention it just here. Now, what I want to focus on for the next slide is actually going away from numerical relativity and look at the post-Newtonian calculation that we have done with Banafsheh Shirali-Lu at the University of Amsterdam, Tanja Hinderer, who you saw just before me, Samaya Nasanka in Amsterdam, and Nestor Ortiz in Mexico City. And here, what Banafsheh has done is calculating using post-Newtonian methods, the gravitational waveforms outside the small coupling regime up to 0.5 post-Newtonian order beyond the leading order for the scalar field, and 1 PN order for the tensorial modes. And what I'm showing you here on the top is H plus polarization as a function of time. Down here, the frequency evolution as a function of time. To be specific, we chose a black hole binary, again with a mass ratio of 1:2, no spins, and we set the total mass of the system to be 15 solar masses. And we are now, because we are outside the small coupling regime, we actually had to specify what this dimensionless coupling alpha GB over m squared is. And what we can see here are the gravitational waveforms computed in general relativity in black and in this Gauss-Bonnet gravity here in blue. And we're starting here at the beginning at a frequency of about 10 Hertz, which is comparable to the lower end frequency of the LIGO sensitivity band. And the main message that I want you to get away from this here is that we see the gravitational waveform is shifted in phase as if you have Gauss-Bonnet gravity as compared to the GR waveform. And the reason is connected to what I showed you before, that our black holes now carry scalar charges. So as they in spiral, scalar radiation is emitted that carries away energy from the system, and that then leads to a faster in spiral, faster increase in the orbital frequency, which then also translates into a higher or faster shift in the gravitational wave frequency. And this is precisely what we see here. And I'm showing this even though it's not a numerical relativity, a calculation, because this is I think it's really impressive. So the first work studying just the scalar radiation is from about 10 years ago, was led by Kent Yagi and collaborators. And it took about 10 years to actually get the first explicit gravitational waveforms in this theory, because it's such a hard calculation. And Banafsheh, who has led the project, did that during her first year of the PhD. So if you want to hear more details about that, about this calculation, I strongly advise you to invite her for a seminar. I should also say that more recently, Kent Yagi and his group has extended this calculation. And I believe he may tell you more about this in his talk. Good. So that's what I wanted to tell you about this type 1 series. And let me take the last 5 minutes that I have for results in this type 2 theory. So just to remind ourselves, type 2 was this kind of coupling where we have coupling function equals to phi squared. In this case, our scalar field equation again becomes a Klein-Gordon type equation for the scalar field with an effective mass squared term. And as before for the neutron stars, we see that if this mass squared becomes negative, then we have a tachyonic instability, and our black holes now can be scalarized. To give you an example, I'm showing here a plot done by Hector Carrera Silva and collaborators, where you have the coupling constant. In their paper, they called it eta. Don't worry about the actual naming. Here we have the mass of the black hole in units of solar masses. And the white regions here are those regions where we still have the Schwarzschild or Kerr solution relativity. And these bands here correspond to scalarized solutions where we have the tachyonic instability triggering the scalar field. So in this case, you see the coupling constant is always positive. If you add rotation to the black hole, then the Gauss-Bonnet invariant, which enters in this effective mass term, can become negative outside the horizon for sufficiently rapidly rotating black holes. So you can have a second scalarization regime when the second derivative of the coupling function or this coupling parameter becomes negative. And this is what's called spin-induced scalarization, was first identified by Alexandru Dima, who is now a postdoc in my group. Good. So let's look at the phenomenology. If we take these black holes that can be spontaneously scalarized and put them in a binary. And what would we expect to happen? So when we started out the project with Hector, we actually thought along the lines of what we've seen for the neutron stars in the very beginning, that we would have some dynamical scalarization as the black holes collide. So we looked at 4 different scenarios, and we identify them here with these Feynman-like diagrams that we have as input either not scalarized black holes, so this would be the S bar. One case where we have one black hole scalarized, not scalarized, the other one is scalarized. And we also had cases with both black holes scalarized initially. And so the first thing, looking at these 2 black holes not scalarized, where we were looking for this dynamical scalarization, we were disappointed at first because we never found a regime where the black holes would scalarize. And to see that a little bit more clearly, let's actually look at an animation of the case where we have 2 black holes. One is scalarized, the other one is not. And we are just colliding them head on. So think of that as a toy model of what we might see. Yeah, so here again, we have the equatorial plane, just a head-on collision. The white lines here are isocurvature regions of the Gauss-Born invariant of our background spacetime. And let me just run this again to explain everything that you see. And here the color coding is again the scalar field. So we have one black hole with a lower mass scalarized, the larger black hole not scalarized. And as they merge, they form a larger mass black hole. Larger mass means smaller curvature. And in fact, the curvature is so small that it no longer supports the scalar field, and the scalar field just dissipates. So instead of dynamical scalarization, we found dynamical descalarization. Yeah, so you may have, in this case, scalar field present in the in-spiral close to the merger, and then it dissipates after the merger. Good, so this was a head-on collision. If you want to see any of the other animations, you can find them here on our YouTube channel. And let me just finish. So this is the last slide with results, 2 more animations where we actually look at the case of in-spiraling binaries. And we have the coupling parameters such that we would have spin-induced scalarization. So the first case that I want to show you is, again, a case of descalarization, where we start with 2 black holes, and the spinning black holes spin anti-aligned with the orbital angular momentum, orbiting around each other, forming a final black hole with a spin aligned with the orbital angular momentum, but below the threshold for spin-induced scalarization. So let's see what's happening. So we actually, again, showing here the equatorial plane and the plane perpendicular to the equatorial plane. The black dots here are the apparent horizons of our black holes. The white lines are the isocurvature regions for the Gauss-Born invariant. And we started with a scalar field perturbation, and you see the scalar field growing during the in-spiral and now dissipating, descalarizing after the merger. Good. So that was one case. And hope you're still with me, because the last case, I think, for me is the most interesting one, in the sense that we start with 2 black holes that are not scalarized, not spinning initially, and they in-spiral about 10 orbits before they merge, and they form a final spinning black hole. So can we have spin-induced scalarization in the merger, and when would the scalar field actually appear? When would this scalarize? So here again, the equatorial plane. Black dots are the parent horizons of our black holes. White lines are the isocurvature regions of the Gauss-Born invariant, and the color coding is the amplitude of the scalar field. And you can see, as I said, we have non-rotating black holes. There's currently no excitation of the scalar field, so this evolution is maximally boring because there's no additional radiation as compared to GR. Now our black hole merges, and still no, so it takes now about 100 light crossing times before we see the scalar field actually sufficiently growing to become visible. So this is a case where we have a modification to general relativity, but it remains hidden during the entire in-spiral and even during the merger, because the tachyonic instability, the growth rate depends on the coupling and grows, in this case, relatively slowly. So only when we cranked up this coupling to values that I would consider non-physical could we see a rapid growth of the scalar field. Yeah, so here it's really a case where non-GR effects will not show up during the inspiral. Good. So with that, let me summarize, because I think I'm also already out of time. So what I wanted to show you today is that we do have numerical relativity calculations in some extensions of general relativity. I would call them proof of principle simulations that have shown us new phenomenology. And looking forward, what we now need to do if we really want to connect from these theoretical models to gravitational wave observations is to produce complete inspiral merger ring-down models that also includes producing at least a small set of waveform catalogs that we can use. And of course, you may want to expand in theory space as well. And with that, I stop here. I thank you all for listening and take more questions.